Hello everybody, I'm Michiel, and as Stefan said, I work at the Royal Meteorological Institute, and I'm very happy to be back here because last year we were just starting working on LUMI and start working with AI. So in my presentation last year I showed a lot of plans, but today I can actually show you some results. We tried a lot of things, some of them failed, but we also have some pretty nice results, and I'm happy to share them with you today. Of course, this is not my work only. This is the work I do with my colleagues Dieter van den Bleeke and my boss Pieter Monia, and also a master's student from Ghent University, Jeff Philippe. I will start with some background. So for those of you that were here last year, or at least at the user day last year, might be some repetition, but I think it's important to give some background before I dive into the AI part. Can everybody understand me? Is my voice loud enough, or a bit louder? Okay, I'll try to do my best, but I probably will deteriorate during the talk. So also for weather prediction, AI, the rise of AI has been quite disruptive in our field. So what we typically do is what we call numerical weather prediction. So we have our weather model, which is basically we try to numerically integrate the Navier-Stokes equations, and this is mainly the dynamics part of our model. And also we need to take into account all processes that happen on the scales that are typically smaller than our grid, on which we try to solve the equations governing the motion of the atmosphere. And these are processes like radiation, surface processes, or everything that has to do with clouds and precipitation. So it's basically we try to solve an initial value problem. So we need to have an initial state, which we call in our field the analysis. And how do we get this? Well, typically that's through observations. We have all kinds of observations, from observation stations on land to observation stations and sensors on ships. Also some balloon soundings to get vertical profiles. But now more and more we make use of satellites for observations. Of course, these observations are quite sparse, so we don't have observations everywhere on the globe. And also, especially with satellites, we don't observe the needed quantities like temperature or humidity directly. So we need to use these observations to make a good to make the best initial state we can have. Because the better our initial state, the better our forecast will be. So how do we do this? We combine the observations actually with the forecast or previous forecast. And we combine them with observations to have the best possible state of the atmosphere at the current time. And this is a domain of research on its own, which is called data simulation. And once we have the raw forecast, well, people like the forecasters are typically not really interested in the raw forecast because there are some biases or deficiencies in these forecasts, or maybe these models or our models don't predict those variables that are useful for the forecasters, such as for instance, the possibility of hail or possibility of thunderstorms or lightning. And we can solve this by doing post-processing, which is also a research field on its own. Okay, and it's a pretty new field, so we've been doing this for 70 years, and you can see a slow but steady process. So on the x-axis you can actually see the years, and on the y-axis it's the predictive skill of our models, and different colors represent the different lead times. So the blue color is a forecast 3 days ahead, and the red one is a forecast, I think it's 5 days and 7 days and 10 days ahead. And as you can see, I've drawn these red and green lines. So if you take a forecast of today of 5 days ahead, is almost as good, or it's as good as a forecast 3 days ahead from 20 years ago. So typically in our field we say we gain 1 day of predictive skill per 10 years. And it's a slow but steady process, and this is due to the interplay of lots of development. So as you can see, there's no like major breakthrough in this line. There's no sudden spike where the quality goes up. So it's this steady progress is due to advances in HPC systems, so we can use higher resolutions, but also in our solvers we have better understanding of physical processes. We have better observations, so this interplay makes that this is what is called in this paper this quiet revolution. So we've gained a lot of progress, but it has been without any eureka moment, so to say. One other important concept I want to talk about is reanalysis, and this is predicting the past, which might seem stupid or unnecessary, but this is actually quite vital, because what we do is, or what is done is that when you have a very good version of the model, you freeze that model version, and you also take all the observations you have available from the past, and you're actually not interested in the forecast, but you're actually interested in the analysis. So this means that you can create kind of a complete global picture of the past weather and climate. So one example is the ECMWF reanalysis version 5 or era 5. Anybody who has been in contact with anything of climate probably has heard about this data set. So ECMWF, for the people who don't know this, is the European Center for Medium Range Weather Forecasting, and you can see it as the equivalent what CERN is for high energy physics. ECMWF is for meteorology. So we have this reanalysis data set. It's an hourly full 3D status of the atmosphere. It ranges from 1940 up till now, and it has a resolution of around 40 kilometers. And this is really a crucial instrument for climate research. So everybody that is doing climate research basically uses this data set, and it has around this 5 petabytes of data. So this is a huge high quality database, and when you say huge high quality data, you end up at machine learning. So what people have tried is to try to machine learn the weather forecast. And I've put this picture here again because you can use machine learning for data simulation, the model, and post-processing, but I will focus today on the model part. So this has really caused for a second revolution, or a noisy or a revolution, as some people try to or label it. The first attempts were already done quite early in 2018 by Dubin and Bauer. So these were people already from ECMWF. And what you see here again is on the x-axis is the date of the publication, and on the y-axis is the skill relative to the IFS HRES, which is believed or is typically regarded as the best global weather forecasting model. And the first attempt was really simple. You have one variable is D500, so it's the pressure, or it's equivalent to the pressure at a certain height. And you try to basically forecast the next time step, so 1 hour later. And you do that by basically very simple MLP, or fully connected neural network. So that's what they tried. And as you can see, results were encouraging, but nowhere close to what the NWP was providing. So just to give an overview of what they tried to train 60 million parameters to have this 1,800 outputs. So these 1,800 outputs are basically all the grid points you can see there on the bottom right. So it's a huge amount of parameters you needed to train for just a very limited amount of output. And then there were some early attempts, which gave some increase, but still these machine learning models were not able to compete with the numerical weather prediction. And this led to some bold claims by quite respected people in the field. Basically, it boils down to, in theory, it's possible to machine learn the weather forecast, but with these 5 petabytes of data, we basically don't have enough data available to do this and to compete with NWP. But then, of course, there came a breakthrough, basically 2 papers. There was the ForecastNet paper from NVIDIA, which really showed that you could scale up these models, because all the red and green models, they basically were working on quite low resolution, and ForecastNet was the first model that could really work at this high resolution, so these 30 kilometers that was provided by ERA. And then Keisler, he really introduced a new architecture, or basically looked at literature and applied existing architectures to the problem of weather forecasting. And I will go a bit deeper into this, what he used, these graph neural networks, because they still form the basis of what we are doing at RMI today. So the idea is that you have the 3D state of the atmosphere, so you have all your grid points, and on each grid point you have all your grid point you have your meteorological variables at different also vertical levels. So what's stated here as the 78 channels, you can see them as really the meteorological variables. And then you encode these variables to this latent state, and actually you do the opposite of what typically an autoencoder does. You actually increase the number of channels, so you don't compress, but you expand. But in the meanwhile, you go to a lower resolution. So this 3D state of the atmosphere is at a high resolution, but this latent state, it has a much lower resolution. And then in this latent state, you try to learn the time step. So you want to move forward one time step, and then afterwards you decode again to the actual atmospheric variables. And how does this work? And to do this, it uses a message parsing architecture. And how does that work? So you have your grid nodes where your physical variables live. You have your mesh node where your latent variables live. And you connect them through these edges. And what you do is you first update the edges by gathering information on the edge itself, the grid node and the mesh node. And you update the edge basically also through an MLP, by training an MLP. And then once the information is actually moved from the grid node to the edge, then collecting all the data or the information on the edges, you update the mesh node. So this allows you to transfer the data from the grids from the physical grids to the processor mesh, so the orange blobs. And then basically you can do the same thing for the processor. So you first update the edges based on the information of all the connected nodes, and then you update the node by gathering and learning the function to update the central mesh node, and then same for the decoder. So basically this is the principle of message parsing graph neural networks. And here you can see you only need to train, or what Keisler did, he only needed to train 6.7 million parameters to get around 5 million output. So much better use of the data that's available. And then big tech was also waking up. So then you have other companies that were getting interested, like GraphCast is the model that was developed by Google, which is basically the Keisler version on steroids. And then you have also Fuxi Fengwu, which are from Chinese universities, and the Pangu Weather, which was by, what's it called, Huawei. And then you can see here AIFS, which is the AI version from ECMWF. There's quite a big gap in time, because at the point here, end of 2023, or mid-2023, like our whole community was still under the impression that, well, we don't need to worry about AI. Our problems are still too complex to be tackled by AI, but we were wrong. And actually, ECMWF did quite an impressive job in catching up with these latest developments. And as you can see here, so this figure I made myself, and I kind of ballparked the values, and somebody did a much better job than me in showing all the skill of all these different models. And you can see really huge amount of models have been developed. So it's definitely more than a hype. A lot of research institutes, a lot of big tech companies, lots of national meteorological institutes are heavily investing in this. And you can see also here, if I bring up this quiet revolution figure again, you can see really a step change. We've gained 10 years of traditional developments in 1 or 2 years. And as you can see here, from some other presentations, from Peter Dubin, who is head of the Earth System Modeling section in ECMWF. He says, yes, AI is part and emphasis of part of the future of weather and climate modeling, and also the head of research from Met Norway says it's the end of the world as we know it, but I feel fine. Okay, so then the question was for us at RMI, how do we compete, or how do we go about this whole AI revolution? Because I don't think it's anything politically incorrect to say we have only limited budget at RMI. We already have quite a small research department as it is, and now we also have to include AI. So we were kind of scratching our heads, what should we do about this? And this is where ECMWF really took us by the hand, and they developed Anemoi. And Anemoi is a machine learning framework. It's Python-based that really allowed us to supercharge or to really, without much experience ourselves, start doing machine learning. So Anemoi, it's a reference to the Greek mythology. They are the ghosts of the wind, which explains my title, Catching the Wind. And it's a framework, so it provides a complete toolkit to develop data-driven meteorological forecasting, covering the whole machine learning lifecycle. So it covers everything from building the data set, doing the training, doing development, then also deploying our models into production, and also then cataloging everything, doing the logging of all the data that you used and which checkpoints you're using and so on. And also important, it's open source, so it's developed through a European collaborative initiative. And last year we also won this EMS, so the European Meteorological Society Technology Achievement Award. Bit more about Anemoi. So it's basically 5 Python packages, modular, so it's very modular. You have Anemoi datasets, which converts your NetCDF, so all the data formats that are typically used in earth sciences, to machine learning friendly datasets. Then you have Anemoi models, which allows you to build your model. Anemoi graph, it allows you to build your graph, since we are mostly focusing on graph neural networks. And then Anemoi training, which combines your dataset model and graph to do the training. And then finally, once you have trained and you have a checkpoint you're happy with, you can use Anemoi inference to make actual forecasts. As I said, it's open source. But of course, we didn't, or people at ECMWF, and we had very small contributions from RMI. They didn't reinvent the wheel, so we rely really on the existing tools. And the main dependencies are PyTorch, PyTorch Lightning, and PyTorch Geometric for building the model, doing the training, and creating the graph. Then for the data handling, it's built around EarthKit, which is another Python package developed by ECMWF, focused on this earth science data. We use ZAR to save our ML-friendly data set, and also make use of X-array. And the interaction with the actual Python code goes mainly through config files, which depend on or use Hydra, and use Pydantic to validate your config, and everything is logged with MLflow. So some of the design choices, so as I said, it's open source, and we focus really on the best use of resources. So for instance, we do not want to starve the GPUs during the training. And also very important is make research to operations as simple as possible. So this is why there's a different package for inference and training, because if you split them, you don't need the heavy dependencies that training needs to do inference. And also each component collects metadata that can be used by others. That means that once you have a checkpoint, all necessary data is in there, what variables do you need, and so on. What version of the code you used, everything is in there, so you can really, especially for operations in weather forecasting, everything needs to be reproducible. That's very important in our field. Okay, so what can RMI then bring to the table in this whole AI revolution, or not specifically RMI, but all smaller national meteorological institutes? Well, there's the fact that all the models I showed before, they basically showed that all these models were trained on the global data sets. And these global data sets is typically the ERA 5, which has a limited resolution of 30 kilometers. But actually, there exists much more higher resolution data sets. An example of this is the SARA data set, which has 5.5 kilometer resolutions and covers 36 years. But it only exists over a regional part it only exists over Europe. And this is what we have been doing at RMI, so making forecasts over limited areas, so we can apply our knowledge there. So what we do is we use this high resolution reanalysis, but complemented with lower resolution boundary, so reanalysis data coming from a global reanalysis, for instance, and then we learn only on the regional domain. So we use the information on the boundary to make a forecast only on this regional domain. What do we use for that? Well, we also use the same encoder, processor, decoder architecture. We use a 6-hour time step, and we use a graph transformer, so we don't use the message passing anymore. We use a transformer, so basically we only give attention along these edges that are defined in the graph. And we end up for this with around 250 million trainable parameters for our latest trained model. And so how do we do this on LUMI? So I might go into a bit more detailed LUMI setup there. So these models, they no longer fit on one GPU, so we use this model parallel. So the model weights are divided over the multiple GPUs, and there we use the 8 GPUs, so we shard the model over a full node. But we also use data parallel. And as our previous speaker also mentioned, that this way you can you have several instances of the model that handle a different batch, and we use a batch size of 1 per GPU, but we want an effective batch size of 16, so we would need 16 GPUs, but we also shard our model over one node, so this basically boils down to that we can use 16 nodes in parallel. We tried going to 32, but then we saw degradation in our loss. So basically, at the end, we stayed with 16 nodes. So a full training takes around 19 days. So if you add them, you end up around 30,000 GPU hours to train our model. People who are quick in math might find out that 128 times 19 times 24 is around 60,000, but I've put here the billing hours for LUMI because if I'm not mistaken, LUMI has 2 chiplets for 1 GPU. So the actual cost is halved. Our LUMI environment, how do we technically work on LUMI? So we use container to build our own container from the base container that is provided by LUMI. And for this we use ROCm 6.0 together with Torch 2.3 plus Anemoi. But as we were training, we also needed to do some developments, especially for this LAM configuration. So there we use also an additional virtual environment. And we have been struggling with some nickel or NCCL timeouts within this all-gather approach. And together with colleagues from Norway, we've dived quite deep into this, but for now we still haven't found out. Well, sometimes we get this timeout. So a training session might run fine for five hours, and then suddenly we get this error. So we make lots of checkpoints or do the regular checkpointing then we can just restart our training. So we also stumbled upon something peculiar. So at some point we wanted to update our software stack, and we want to move to Torch 2.7 because it has some nice new features, but this also requires to update our ROCm version to 6.2, which is available on LUMI. But then we saw suddenly, so in the brown line you see our baseline training curve, but going to this new environment, we suddenly saw some strange behavior in our training loss. And my colleague Dieter actually did some quite deep digging, and we found out that there are, at least to our understanding, some issues with precision handling. So basically we always use this 16 mix. So as also the previous speaker mentioned, that we use 16 bits for the forward and backward pass, and use 32 bits precision for updating the gradients. But if we use this 16 mix with ROCm 6.3, we get this strange behavior in our loss. And by putting just using 32 bits, we can revert back to this brown line you can see here. So if people have also experienced this on LUMI, or if people might know some what's causing this or how to fix this, please, and it would be very interesting to talk about this later. And now, so some results. So what you can see here is an actual forecast using AI of the winter storm Chiara in February 2020. I think it led to around 10 casualties, so it was quite severe. And on the left-hand side, you can see the forecast. On the right-hand side, you can see the truth. So you can see already qualitatively that this is doing quite a good job. And for me, coming from, so I have an NWP background, this is really amazing, because this forecast of 6 days took around 8 minutes using 2 GPUs. If I wanted to do this forecast using NWP, I would need around 1,000 to 2,000 cores, and it would take me 2 to 3 hours to do this forecast. So to see this kind of detail already in such an AI forecast, for me, it's really mind-blowing. Okay, I also have some case studies. So here's the heat wave in August 2020, where you can see you go from, on the 5th of August, from 20 degrees to 35 degrees almost on the 8th of August. I think it was a record that day. And this is our traditional forecast, or Alero model that runs at 4-kilometer resolution. This is typically we only do a forecast up to 2.5, 3 days, because after 3 days the benefit of doing this high resolution becomes negligible with respect to lower resolution global models. And you can already see here these biases that I talked before. So in the case of clear sky, we know that our model struggles with these lower night temperatures. And then this is what we have from our machine learning model. So the advantage of our NWP model is that it has hourly output. For our machine learning model, we only have output so we have a time step of 6 hours, so that's why I've put only these dots there. And you can see already that the machine learning model really captures this nighttime temperature in clear sky, and also really covers these high temperatures. Only the last day you can see that it overshoots a bit this temperature. But then if we compare that to an actual NWP forecast of that we started on the 7th, you can see still machine learning model is doing a better job than the NWP model. But then you can say, okay, that's nice, but you by taking the 6-hour time steps, you're kind of stepping over this highs and these lows, which are probably the most difficult to predict. Indeed, that's what we also thought. And up until now, the idea was that you need to make a big enough time step, because how these models work is they work autoregressively. So they make one forecast, and then they take the output of the forecast as input of a new forecast steps. And the idea was that you need to take your time step sufficiently large, because otherwise, if you have a smaller time step, by doing many time steps, your error growth or your error buildup will just be too big, and you will end up after 3 or 4 days with bad forecasts. But we actually, because the Sarah dataset has 3 hourly data, we actually try to train our model with this 3-hour frequency, and actually we kind of at RMI together with people from Geosphere kind of proved this basic idea wrong. So basically we were able to show that even going to high resolution does not necessarily lead to this buildup of accumulation of error. So you can see that even the 3-hour model performs reasonably well. And this you can also see here in this general score. So you have the root mean square error and the bias of the 6-hour and 3-hour model, which you can see that they are pretty close to each other. And unfortunately, I didn't have time to include also the the NWP model there, but it's around the same or lower, so the scores are better for the machine learning model, and also for another variable. So this was 2 meter temperature, the previous one, and this one is dew potential height, which is similar to pressure at a certain level. We also did some study on comparing this LUMI approach that I just showed with stretch grid, where you actually do a forecast on the whole globe with different resolutions, and this is now this work is now under review, and people that are interested can have a look at the archive. I will not go into detail because it's quite technical. Still, some challenges remain. Also important to talk about this. One challenge is this smoothing. As you can see on the left-hand side, there's a forecast of plus 12 hours, so 6 days ahead forecast, while on the right-hand side you have the truth. And you can see that these fields are quite a bit smoother on the left-hand side. And this is actually a result of the loss function we use. We use mean squared error loss, and there you suffer from what is called the double penalty, where, for instance, if you predict high temperature, or there's a high temperature here and low temperature there, but then you predict a high temperature here and low temperature there, you get penalized here and you get penalized there in your loss function, while you just made a kind of error in the location of your high temperature. And this for the model is then safer to just predict the average temperature everywhere, because this will lead to a lower mean square error. So this is the effect you see here on the fields. But there's a solution to this, and that is going probabilistic, where you use a probabilistic loss function, and you also inject noise into the processor, which allows you to create an ensemble. So you have multiple forecasts for a specific time. So this has already by ECMDF proven to give you much more realistic fields with much more higher detail. And we are now ready to start a training run on LUMI. And what's another good thing is that now in Anemoi we can make use of this Triton kernel, which is a kernel specialized and compiled for the graph transformer architecture we use. So there we gain a 25 to 40% speed up by using this Triton kernel, which will lead to the fact that while we now have to train 4 or 5 models in parallel, we will probably stay at around the same GPU hours needed to train the model. And then the final thing I want to show you is this artifact. So this is if you go to even higher resolution. So this is a picture that was provided to me by Meteo Swiss, where they trained a 1 kilometer resolution model. And there you can see after a couple of time steps, you can really start to see these artifacts, and it's really the processor grid that starts to shine through this in the forecasts. And also here, an example by Med Norway, where you can also see this kind of artifacts, some signature of the processor mesh shining through in your forecasts. And for this, the solution is still unknown, so this is really researched as we speak. First thing was we tried this, maybe there's some overfitting, but it doesn't seem to be the case. And now there's questions, is it the graph transformer architecture we are using, or maybe we need to rethink the decoder? So these are things we are thinking about now. And I want to finish my talk here with this closing remark. And I think it's really important because as RMI, as you see, it's 2 or 3 people working on this, and we are really punching above our AI weight. We have to compete with big tech, with large research institutes, and this is due to 2 things, or maybe 3 things. So we have very dedicated people working on this, and we have international collaboration with Anemoi, and we have the resources to do it to LUMI. So many thanks to LUMI, and yeah, I also had to include some AI slop picture in an AI talk, of course. So thank you for your attention.